This is video 2.4.2, and the objective of this video is to understand how to use synthetic division to find linear factors. We're going to get more into the whole goal of finding linear factors, but right now we just need to know how to divide using synthetic division. So synthetic division is, you can use it instead of long division or instead of factoring and using your generic rectangles to find what it would divide into. So here's an example in what the book shows and what the book talks about. And this can be found, if you want to come back to it, this can be found on page 305 of your textbook. So this compares the two long division and a synthetic division. So some of the things to notice, remember mathematicians, they like to shorten things. They don't like to write a lot. They like to save paper. That may seem crazy because we've used a lot of paper this year, but they want us to save paper by condensing everything that we did in this long division problem over here and turning it into something really short and sweet that you see over here. They basically took out all the extra stuff, all the stuff that makes this a real problem, and just broke it down into the numbers and what was being done with them. And they noticed the pattern of what they do every single time. And they said, quit wasting all this space, let's make it simple. So notice some things that reoccur. We'll talk about how they got all these numbers, but some of the key important pieces here are, notice things like the 53. That is what the remainder was. Okay, notice that the rest of this result is what the coefficients of the quotient were, which is the result after you divide two things. Notice that the divisor, the thing that's dividing in, has been shorthanded into this corner. So that's going to kind of show up in the same spot. And then take a look here at the dividend, the thing that's being divided, is broken out and just taken towards bare bones, just the coefficients of the terms in descending order, descending degree, I should say. So we're going to talk about how to get these numbers and how to break it down. There's some other things that you should notice up here. For instance, the number 3 came up in here, the number 21 came up in here, and the number 48 came up in here. So all these things show up, and they basically, like I said, just took down all the junk and just made it simplified and condensed. So everything that's important is in there and nothing extra is included. So we're going to take a look at this process. We're going to show you what the book has to say. So if you need to look back at a list of notes, this is on page 306 in your textbook. But to start out, to divide a polynomial, at first, number 1 will only work for linear factors. You can only use it when you're dividing something by a linear factor. So you can't divide by x squared plus 2. You can only do x plus 2, x minus 3. So that's why it's really going to help us find factors. And you'll see that in the next section. When we're dividing by a polynomial, notice that it's only, this algorithm works for x minus c. So we're going to work with that in just a moment, but let's take a look at the first step. The first step is to arrange the polynomial in descending powers with a 0 for coefficient of any missing term. Do you see the term that we're missing here? We have a coefficient of 1 for x to the third, but we do not have x squared, so we need to insert a 0 there. And then we have a negative 7 and a negative 2. So that's going to be the dividend that's being divided. Now the c for the divisor has to be when it's in the form x minus c. Well, we have really x plus some number. So we have to rewrite this as x minus a negative 2. This is going to be the small trick that some of us are going to forget, and we're going to need to be careful and remember that. It should be in the form x minus c, and if it's not, we need to create it that way. So we're actually going to use negative 2 in our corner here, and we're dividing everything out by negative 2. That's really important, or you'll get the wrong results here. We'll draw our line to represent our equal sign, and then we'll start the process. Okay, so we did this. We did the leading coefficient of the dividend on the bottom row, and we wrote the coefficients of the dividend. Now, here's what we're going to do. We're going to drop this leading coefficient of 1 down. That's always your first step. Now we're going to follow this process that will be repeated until you end. You're going to multiply this number by the c value. So we always multiply, and we'll get negative 2. and we'll write that in here. So we multiply and insert. Then we add. 0 plus -2 is -2. And now we repeat the process. So instead of multiplying -2 by 1, we're going to now multiply -2 by -2. We get +4, and we're going to insert that here. Then we'll add and get -3. And we'll repeat this one more time. -2, the C value gets multiplied here. We get +6. And then we add 4. Okay, so we repeated the series of multiplication as they talked about here after multiplying, then adding, and then repeating until we get all the columns filled in. So the number in the last row is the numbers in the last row, the 1, -2, -3, and the 4 are the result, okay? The degree, and how do we decide where the x's go? So now we got to think carefully about where the x's go in these cases. So the x's, here's what's important here. So we have these terms, and these are going to be our coefficients of our quotient, our result. So these are going to be the coefficients. So it's going to be 1 times x squared. And how did I know it was x squared? Well, I always take the degree of my original polynomial and I drop it down 1 because I'm dividing it by an x polynomial. So of course, the only way to get x to the third is to do x times x squared, which is why it has to be x to the third here. So I have 1x squared minus 2x minus 3, and then I realize I'm out. I'm out of x powers. So my 4 is actually my remainder. So plus 4 over the dividend, x plus 2. Or the divisor, the divisor, x plus 2. So I'm left with my result. That's my answer, x squared minus 2x minus 3 plus 4 over x plus 2. That is the result after dividing those two polynomials. So this process will work the same as factoring, the same as using your generic rectangle or using long division. It just takes away a lot of the space. So you're going to try it and see if you like it and use it when necessary. But here's a couple of reasons why it's nice. So we're going to do one more problem and then we'll talk about why it's nice. So let's take a look. So we got to remember, we first write our x minus c term in the top corner. This is already written in x minus c form, so we can see that c is 2. Then in descending order, so starting with the highest going down to the lowest, it's already written that way. We write the coefficients, 1, -4, 5, and 3. Okay, we draw our result line. And we start by dropping the 1. We do 2 times 1 to get 2. We add -4 plus 2 to get -2. That's our first one. Now we do it again. Now we do -2 times 2 to get -4. We add the 2 together to get 1. One last time, we're going to do the 2, the c value, times 1 to get 2, add the 2 together to get 5. So my result for this one is, once again, we take this power and we drop it by 1 because we're dividing by a power of 1, and we'll get 1x squared minus 2x plus 1 plus 5 over x minus 2. The remainder always goes over the divisor. So here's why this is an interesting process. Here's where synthetic division is a nice thing to know because it allows us to calculate things quickly. So if we had to calculate things quickly, we could using this process. So let's take a look at what's called the remainder theorem. The remainder theorem. The remainder theorem is an interesting case because here's what happens. If we were actually trying to find, so let's think about what we're doing here. We're taking this function and we're dividing it by a value of x minus c, right? So what's going to happen is we're going to get an answer of, I don't know, some quotient q plus the remainder, right? There's always some remainder that we had to add on, okay? So what we're saying here is that f of x could be written as the product of x minus c, the product of this guy, times some number. Because remember when we divided this, we got a quotient, an answer for the quotient, the result, some number, some polynomial. So if I were to multiply that back out again, I would get this quotient. But I have to add on that remainder because there was that extra piece that didn't quite fit. Just think about your generic rectangle, that piece that didn't quite fit in the generic rectangle. So here's why understanding this is important. If I wanted to find the value of f at c, I want to know, okay, how big is it at c? So in our case, I want to know what's the value of the function at 2. Well, I could do some boring things and I could plug in 2 to this function here. This is my f of x in this case. I could plug in 2 and do all this great work. 2 to the third minus 4 times 2 squared plus 5 times 2 plus 3. I could do all that math, do it in my calculator, do it in my head to get a nice clean answer. Or I could tell everyone right now that the answer is 5. And the reason the answer is 5 is because of this quotient theorem. So f of c, let's take a look back at this remainder theorem, and see what happens. If I want to know f at c, so everywhere x is, I'm going to put c. C minus c times the quotient of x plus, quotient of c, plus the remainder at c. Okay, and it's some constant out there, some number, some remainder r. I'm going to see that I will get an answer of, well, hey, this whole thing is going to evaporate because this is 0 right here. C minus c will be 0 for every c in the world. So that's going to go away. So my answer will always equal my remainder at that divide when I divided by c. And in our case, remember our remainder? Our remainder over here was 5. So that means that f of 2 will be 5. Now, this was all trying to help you explain the why. But here's the thing you need to know and use in the class. The thing you need to know is that if a polynomial is divided by x minus c, then the remainder is the function at c, okay, every single time. So going back to example 1, if I wanted to know what was this function at -2, remember c was -2, I could quickly say that it's 4 because that was my remainder when I divided by x minus -2. So if you're not sure about that, you can plug in -2 to the third power minus 7 times -2 minus 2. And see that you get a value of 4. So at some point you're going to have to do the work. The question is, do you like synthetic division enough to use it to allow you to find the function at certain values? This will work for polynomials that are to the 5th, to the 6th, to the 12th, and any higher power that you want, as long as you're always dividing by x minus c and using synthetic division to do so. So take a moment, you're going to try these checkpoints, definitely come back to these problems and these examples to see what we're talking about, but you're going to try some checkpoints to see to find the exact values and to try dividing using synthetic division. Okay, here they are. Give them your best shot. Number 3 should be fairly doable. Number 4 has a couple of things you need to take care of before you can use the synthetic division process. And number 5, take quick notice how similar it is to number 4. So use that to help you quickly do number 5. But bring in your questions into class. We'll definitely be practicing this together and getting questions answered so we can clear anything up.